In this video, we're going to discuss using double integrals to find the mass and center of mass. More specifically, we're going to find the mass and center of mass of the region that is bounded by the line y equals 2x and the parabola y equals x squared, given that the density function rho is equal to x. The very first thing that we do in a problem like this is we sketch the region and we make sure to include enough detail so that we can determine the limits of integration. So from here, we sketch the curve y equals x squared, which is the blue curve, and y equals 2x, which is the red line. Now, we need to find the points of intersection, represented by the red dots. It's clear that the first point of intersection is 0, 0. We can find the second point of intersection by setting the two curves equal to each other. That is, setting y equals 2x equal to y equals x squared, so x squared is equal to 2x. By doing this, we see that x squared minus 2x is equal to 0, which factoring in x gives x times x minus 2 equals 0, and now we can use the zero product rule to determine that the two boundaries intersect at x equals 0, which we knew would happen, and at the point x equals 2. And notice when x equals 2, we have that y is equal to 4, because 2 times 2 is 4, and 2 squared is 4. We can now set up our integral for mass. The equation we use for mass is the double integral, m equal to the double integral over the region D, with the integrand being the rho function of x and y. Well, from the previous slide, we know that we have the y varying from x squared to 2x, and that the x varies from 0 to 2, and for the rho function, we just plug in what was given in the problem, which is rho of xy is equal to x. From here, we just evaluate the inner integral as we usually would for a double iterated integral. So doing this, we obtain that our mass is equal to 4/3. So once again, to find the mass, we always just need to compute m equals the double integral over the region D of the rho function. This is hardly any different from calculating other double integrals over a general region. The only difference here is that the rho function is used as the integrand. Now, to find the center of mass, we use the two following equations for x bar and y bar. So x bar is equal to the moment with respect to y, the y-axis, divided by the mass, and y bar is equal to the moment with respect to the x-axis divided by the mass. So x bar is equal to 1 over the mass times the double integral of x times the rho function of xy, and y bar is equal to the double integral of y times the rho function of xy. So since we already have the mass, we just need to find the moments with respect to y in respect to x. So let's find those. That is, we need to find the double integral over the region D of x times the rho function and the double integral over the region D of y times the rho function. So the moment with respect to y is equal to the double integral over the region D of x times rho, which our limits on our integrals are the exact same as they were in the mass calculation. The only difference is, for this one, is that we're multiplying by an extra x. So now we just compute this as we normally would a double integral. Doing so, we see that the moment with respect to y is equal to 8/5. So now all that's left is to find the moment with respect to x. This is equal to the double integral over the region D of y times the rho function of xy. So once again, the limits are the exact same as before. The only difference is this time we're multiplying by a y. So we calculate this as a typical double integral over a general region, and we get to the answer of 8/3. So now we just plug in the values that we found. So since x bar is equal to the moment with respect to y divided by m, and we just found that the moment with respect to y is 8/5, and we already had that the mass was equal to 4/3, we know that x bar is equal to 8/5 divided by 4/3, or 6/5. And similarly, y bar is equal to the moment with respect to x divided by the mass. So 8/3 divided by 4/3, or equivalently 2. And this concludes finding the mass and the center of mass of our desired bounded region. So for future reference, all of these center of mass problems are generally the same. Typically, the only differences are that the rho function may vary and that the region that we integrate over may be different. Aside from that, all this is a double integral as we've seen them before.